Alrighty, hello. We are going to walk through how to solve an ordinary differential equation. And in this particular case, we're going to solve a second order differential equation. So we have here, we have an example problem that we're going to walk through. So we have y double prime plus y prime plus 1.25y is equal to 0. And then we're also given some initial conditions here. Y of 0 is equal to 3. And here y prime of 0 is equal to 1. So the first thing that we want to do when solving this equation is we want to try and find a function with a property where the second derivative is the same as the function itself. And so what that would look like is we're going to set, there's one function in particular that does this from calculus, and it's y is equal to ER of t. So we know that taking the derivative of e to the RT is essentially just the same derivative. So next what I'll do is I'll take the derivative of this, which is y prime, RE to the RT, and then we'll take the derivative of that, which is just r squared e to the RT. Next, we want to get our equation in the form of what's known as the characteristic equation. And so that's going to look something like this, where we have AR squared plus BR plus C, all of that times e to the RT is equal to 0. One important thing to note is that e to the RT cannot be equal to 0. So therefore, we know that AR squared plus BR plus C will be equal to 0. And then A, B, and C right here are all the constants, coefficients in front of our values. So C, for example, is 1.25. B is technically 1 here, and then A is technically 1 right here. And what I did is I just replaced these variables here, y double prime, with the r squared e to the RT. I replaced y prime with r to the r to the ERT, and then y with ERT. And so that is how we got our equation essentially in this form, factored out the ERT, and then and now we're going to go ahead and try to solve this. So now that we have our general equation in this form here, we're going to go and use the quadratic formula to solve for our r. So in this case, it's 1 times r squared plus 1r plus 1.25 is equal to 0. And then we know the quadratic formula is -1 plus or minus the b squared, which is just 1, minus 4a, which is just 1, and then c, which is 1.25. All of this gets square rooted, divided by 2 times a, which is just 1. So if you do the math on this, you'll notice that in the what's known as the discriminant here, we will actually get a negative value under the square root symbol. And so what this means is that we're going to have a complex root to our solution. So we have -1 plus or minus. This is just 4i square, or I'm sorry, it's -4, and the square root of -4 will be 2, and then the negative sign will give us an I value, and this will be all over 2. So one more step, we're going to get -1/2 plus or minus I, because 2 divided by 2 is just 1. Okay, so now we have our complex root, which is r1 and 2 is equal to this. And so one thing we want to notice, or bring attention to in order to be able to solve this differential equation, is we need to use Euler's formula, which is just, so we can say Euler's formula, which is just this expression here. So it's e to the IR is equal to cosine of t plus I sine of t. And so this comes from a Taylor series expansion, which I won't go into detail here, but basically this is the formula that we need to use in order to solve our differential equation. Alrighty, so next what we have is we have a general expression for our differential equation. So now we have y of t is equal to c1 e to the negative 1/2 t times cosine of t plus c2 e to the negative 1/2 t sine of t. So what we need to do is we need to solve for these constant coefficients in front of these values here. And the way that we do that to solve for C1 and C2 is we go back to our initial conditions given here, and we solve for those expressions. So right here we have y of 0 is equal to 3. So what I can do is I can say y of t was now 3, and then everywhere I see a t, I just plug in a 0. So e to the 0 here, because t, 0 times negative 1 is just 0. Cosine of 0 plus c2, and then e to the same thing, 0, and then sine of 0. So we know that sine of 0 is just 0, so this whole term will go to 0, and then we're left with 3 is equal to c1. E to the 0 is just 1, which I won't show here. And then cosine of 1 is also just 1. So we see here that c1 is equal to 3. Now, next, we need to solve for C2. And in order to do that, we actually will have to take the derivative of this y of t expression that we have right above here. So we'll do that next. So y prime of t is equal to, I'm going to rearrange some things here. So we have e to the negative 1/2 t, c1 cosine of t plus c2 sine of t. And so now we have two expressions, the same variable multiplying each other. So we're going to use the product rule and ultimately the chain rule to do this. So the product rule just says that we'll take the first function. Sorry, let me rewrite that. First function times the derivative of the second, and so in this case, that is going to be negative c1 sine of t plus c2 cosine of t, and then this is plus the derivative of the first times the second, and so in this case it'll just be negative 1/2 e to the negative 1/2 t times c1 cosine t plus c2 sine of t. Okay, so after we get to this point here, we will do, I'm just going to rearrange this really quick. So y prime of t, let's see, so let's put this, we'll get e to negative 1/2 t cosine of t, which is, sine 2 minus 1/2 c1. So there's that, plus sine of t times negative c1 minus 1/2 c2. Okay, so now what we'll do is we're going to take our second initial condition, which we had right here, and we're going to plug that in for our variables. So y prime of 0 is equal to 1, so we're going to say 1. And then anywhere there's a t, we're going to plug in 0. So 1 is equal to e to 0 of cosine 0 of c2 minus 1/2 c1 plus sine of 0 minus c1, minus 1/2 c2. All right, so what we have here is, e to the power, anything raised to the power 0 is just 1. So always keep that in mind. Sine of 0, we'll just cancel out this whole term and become 0. So then what we have is 1 is equal to, and then cosine of 1 goes to 1. So then we get glitching here. Okay, so now we get C2 minus 1/2 C1. And so earlier we found C1 to be 3. So really what we get is C2 minus 1/2 times 3 is equal to 1. So this gives us C2 is going to be equal to 5 halves. So so now we have C2 and we are done with our solution. So now we have a general solution for our differential equation, which is going to be y of t is equal to e to the negative 1/2 t, all times 3 cosine t plus 2.5 sine t. And so that's our general solution. And so if you were interested in plotting this, you would see that the following. Let me just switch my screen real quick to Desmos, which is just a graphing program. Okay, so there we go. Let's go here. Okay, so here we graphed our function, and we have its the expression that we had earlier, which is just, let me get out of here with that. So just the general solution that we found earlier, and we see that it is exponentially decaying, and that's because we have a negative factor in our expression. So going back to sorry, this thing is so. Oh, there we go. That works. All right. So going back to our problem here, one thing to note is that in our complex root here, we had a negative real part. And so this determines whether you have exponential growth or so you either have growth, decay, or decay, or just constant oscillations. And so if this is greater, if the real part is greater than 0, if it's positive, you'll have exponential growth. If the real part is less than 0, you'll have exponential decay. And then if the real part is equal to 0, then you just would get constant oscillations, for the life of the system. So just something to keep in mind. But anyway, so that's how we kind of walk through how to solve an ordinary differential equation, and one specifically when it's a second order, along with when you get complex roots in your solution. So thanks.